In the previous video, we learned that the change in entropy of the universe is calculated from the change in entropy of a chemical reaction, the enthalpy of the reaction, and also the temperature. In this video, we're going to begin by doing some algebraic manipulation to this equation to come up with something that's just a little bit cleaner to work with. So the first thing that we're going to do in this equation is get rid of the temperature in the denominator, and we're going to do that by multiplying every single term in this equation by T. So we're going to say T delta S of the universe is equal to T delta S of the reaction minus delta H of the reaction. And again, we just did that to get the temperature out of the denominator. Now what we're going to do next might not make a ton of sense, but it's, hey, it's what we've done, what chemists have done. We're going to go through and change the sign of every single one of the terms in this equation. So we're going to say negative T delta S universe is equal to negative T delta S of the reaction plus the delta H of the reaction. And then one last step that we're going to do here is just to reverse the order of the terms on the right-hand side of the equation so that we have a positive minus a negative instead of the other way around. So for one last step here, we're going to say negative T delta S of the universe is equal to delta H of the reaction minus T delta S of the reaction. And if this is under standard conditions, we can go along and put the standard symbol on all of these terms if we would like to do that. It's not necessary, but I'll go ahead and fill those in. Now, this left-hand side of the equation, negative T delta S universe, chemists refer to this as Gibbs free energy. It's given the symbol capital G, oftentimes delta G, because we're talking about a change. And again, this is referred to as Gibbs free energy. Specifically, it's going to be Gibbs free energy of a reaction. And mathematically, delta G is equal to negative T delta S of the universe. But calculating the delta S of the universe is a little bit tricky. There's a lot of steps involved, so the delta G is just a shorter version of that. Using this term delta G in place of negative T delta S gives us a new equation, delta G of a reaction is equal to delta H of a reaction minus T delta S. And this equation that I'm writing in blue, I'm getting from the right-hand term here. See that I've just copied it straight down, and I've just used a delta G in place of this negative T delta S portion. So that's where this equation comes from. Under standard conditions, we can absolutely put these standard states on there. A lot of times, the reaction abbreviation, the reaction subscript has been left off of these terms, so it just is simplified in this format. So you might see it written like that, but all of these terms, the delta G, the delta H, and the delta S, they are all referring to the conditions of the reaction. So let's now take a look at the spontaneity, how we can use these different terms to predict the spontaneity of the reaction. Starting up here at the top, in the previous video, I told you that a reaction or a process was spontaneous when the delta S of the universe was a positive number. So we're just going to say delta S of the universe is greater than 0. When we algebraically manipulated this equation right here, the left-hand side of the equation, as it was originally written, needs to be a positive number. When we multiply temperature by this positive number, this side of the equation is still going to be a positive number. Temperature is always positive in this equation, never a negative number. That is because the temperature unit that is used in this equation is the Kelvin, and there's no such thing as a negative temperature on the Kelvin scale. So a positive temperature times a positive delta S universe means that this left side of the equation needs to be positive or greater than 0 for the process to be spontaneous. Now in this next step, algebraically, when we put this negative sign in front of it, we actually changed the conditions of the left-hand side. So putting that negative sign in front, negative T delta S of the universe, in order for a process to be spontaneous, this number needs to be less than 0, or a negative number. Let's think about that a little bit more specifically. So we said that this number here needs to be positive for the process to be spontaneous. Temperature is always going to be positive, so positive times positive, process spontaneous when T delta S is positive. Here we have a positive temperature still, we have a positive delta S of the universe still, but we've thrown this negative sign in front. And so this whole entire term is going to need to be a negative number when the reaction is spontaneous. Because delta G is defined as negative T delta S, then, most importantly, as we get down here, for a reaction to be spontaneous, delta G needs to be a negative number or less than 0. It is non-spontaneous when delta G is a positive number or greater than 0. And a new term, a process is in what we say equilibrium when, got an extra L in there. A process is in equilibrium when delta G is equal to 0. Equilibrium means that the reaction is not necessarily moving in a directly forward direction, but it's got some sort of balance in it in moving forward and also moving in reverse. We'll talk more about equilibrium processes in the next couple of videos. But the value of delta G, negative for a spontaneous reaction, positive for a non-spontaneous reaction, and delta G is equal to 0 for a reaction that is in equilibrium. One last thing that I want to say about the value of delta G is that it can be calculated using Hess's law, just like delta H and delta S. So if we have this delta G equals delta H minus T delta S, and let's make a note here that we can calculate delta G either by solving the right-hand side of the equation, or we can calculate delta G using Hess's law. Just like we could calculate all of these terms using Hess's law. So kind of just sort of depending on what kind of data is available to us, we have a lot of different options for calculating this. Let's look at one example of using Hess's law to calculate the delta G of a reaction. Let's say that we have hydrogen gas with chlorine gas reacting to produce 2 HCl molecules in the gas phase, and this reaction is taking place at 25 degrees C, which is our standard temperature. Because this reaction is occurring at standard temperature, we can use standard delta G values for all of these terms. If we look them up in a table, we'll see hydrogen gas has a delta G of 0 kilojoules per mole, chlorine, same thing, 0 kilojoules per mole, and HCl delta G value is negative 95.27 kilojoules per mole. If we wanted to calculate the delta G of this reaction using Hess's law, we would simply use the formula products minus reactants, each multiplied by their stoichiometric coefficient. We've used Hess's law so much, I don't want to spend a ton of time going into how we're using Hess's law or exactly what's going on here with this calculation. If it's unfamiliar to you, just back up and look at some earlier videos where we describe how Hess's law works. And this is going to give us a delta G value of negative 191 kilojoules per mole. Because it is a negative number, this tells us that this is a spontaneous process.